Hello everyone. In this video, we will be discussing about a derivation that is on stresses in helical coil springs of circular and non-circular cross section. So the derivation, firstly, we will be discussing about stresses in helical coil springs of circular cross section, and while discussing the derivation itself, I'll tell you what are the changes to be done for the non-circular cross sections. So, as we are very much aware, in the previous video also we have discussed like how a circular cross section spring would be and what are the major terminologies to be remembered. So, first let us consider a helical compression spring made of circular wire and subject to an axial load W, where capital D is nothing but mean diameter of the spring coil. As we know that capital D is nothing but exactly from the center point of the left side of the coil to the to the distance of right side of the coil. So that is nothing but capital D, and small d is nothing but diameter of the spring wire. Since I am talking about the cross section, circular cross section, the diameter will be there, and that is denoted as D. So we were here talking about non-circular. Say for example, if it is rectangle or if it is square, so we need to consider what is the width, what is the length, and what is the like a thickness. So all those things we need to consider in case if it is a non-circular condition. And small n will be the number of active coils. So if you consider a spring means it may be like a multiple coils will be like 7 coils, 8 coils, 9 coils. Out of all those coils, how many coils are very much effective, that we need to check it. And next one, capital G, and this number of active coils usually vary from like application to applications. For example, a heavy load is suddenly applied means all the coils will be definitely active, but similarly when a small load is applied over this coils means what happens, only on a few coils the load will be there. And capital G is nothing but modulus of rigidity for the spring material. And as we already assumed here, the load which is applied on this spring, that is axial load, that is capital W, and tau I'll be calling it as the maximum shear stress which is induced in the wire. And capital C is nothing but spring index, which we are discussed already in the previous video, which is also equal to capital D by small d, that is mean diameter of the spring coil to the diameter of the spring wire. And P is nothing but pitch of the coil, and most of the cases the pitch remains same. And finally delta, that is nothing but deflection of the spring, and which is nothing but a result of the axial load W. So all those things we can able to see here. A spring which is of the circular cross section, where small d is nothing but wire diameter, and capital D is nothing but the mean diameter, and W is nothing but the axial force which is applied. So here I will be considering a compressive force. So a compressive force which is applied on a axially loaded helical spring. And if you see the like the free body diagram of the same spring means, where you can able to see that in the one side we can able to see that where a tension and other things also we can able to see here. So a free body diagram showing that a wire is subject to the torsional shear and a direct shear. So both the shears we can able to see it here. And moving to the like the shears and the twisting. So we know that generally the twisting moment capital T is equal to W into D by 2. Here further it is equal to pi by 16 into tau 1 into D cube. So let me write down the twisting moment, that is twisting shear twist, we can call it as tau 1 is equal to 8WD divided by pi D cube. So in addition to this torsional shear stress induced in this wire, the following stresses also can act on the wire. So what are the following stresses may act? That is the direct shear stresses due to the load W, and the shear stresses due to the curvature of the wire. You can able to see this. So the shear stresses which is in the spring wire due to the torsion, and here you can able to see the average shear stresses in the spring wire due to the force F. So here the symbols are not shown, that is the torsion and like the force, but actually you can able to see this. In case of the force means all the force will be uniform from the one end to another end, but in case of the torsion means you can able to see it is vice versa. On one quadrant if it is upside means, and the other quadrant, in the opposite quadrant, it should be downside, but the magnitude of the shear remains same. And you can able to see even the resultant torsional shear and direct shear stress diagram also you can able to see here, where this is the axis of the spring and this is the outer edge and this is the inner edge. You can able to see this. So there will be a variance in the magnitude of the resultant shear. You can able to see the first quadrant where the shear value, the magnitude is more and even the amplitude is also more. But if you look at the opposite quadrant, where the third quadrant, the like the shear value is less, along with the amplitude also it is very less. And here you can able to see the direction. Always in the positive quadrant, the values will be in plus, but in other quadrants, example, you can go with the third quadrant, like fourth quadrant or second quadrant, there are chances we may get the negative values too. And if you see the second one, the resultant torsional shear, where the direct shear and curvature shear stress diagram you can able to see. So in which is again plotted with the axis of the spring and the half of the beam diameter, that is d by 2, because we are looking for only one quadrant. Almost the amplitude remains same in both first and third, but the directions and even the values, there will be a negligible amount of increase and decrease. So we know that the resultant shear stress which is induced in the wire, from the previous relation, let me write down, tau is equal to tau 1 plus or minus tau 2. So tau 1 already we know that it is 8w d by pi d cube, and tau 2 from the relation I will be taking as a result of this resultant torsional shear curvature, it is 4w divided by pi d square. So here the positive sign is used for the inner edge of the wire, because here we have a plus or minus is there, but let me consider the positive sign. So the positive sign which is used for the inner edge of the wire, and the negative sign is used for the outer edge of the wire. Since I will be talking about the inner side, let me consider the positive. Since the stress is maximum at the inner edge of the wire, therefore let me consider the positive one, and the maximum shear stress induced in this wire, which is equal to torsional shear stress plus direct shear stresses. So torsional shear stresses plus direct shear stress, the formula is 8w d by pi d cube plus 4w pi d square. So let me simplify this one. So how to simplify this one? So let me take 8w d by pi d cube common from this one. So first like term you can able to see, since everything is present, it becomes 1, plus in the other side it is 4w by pi d square is there. So let me go with the spring index value, that is a d by d. So with the help of that one, if I go with means, when if I 8w d by pi d cube, if I'm taking again, if I'm taking this inside means, I'll get the 4w by pi d square I will get. So after simplifying this one, the spring index value, that is d by d, so I'll be writing it as 1 by 2c. So which is equal to, under all these terms, let me write as a ks. So it is ks into 8wd by pi d cube. I'm talking about this one. So ks into 8wd by pi d cube, where ks is nothing but shear stress factor. So while solving some problem also, where we will be using the shear stress factor value, that is 1 plus 1 by 2c. So in order to consider the effect of both direct shear as well as the curvature of the wire means, a wall stress factor, that is capital K, introduced by AM wall, may be used. The resultant diagram of torsional shear, direct shear and curvature shear stress is already shown in the previous sketch, where the maximum shear stress induced in the wire can be written as tau is equal to K into 8wt divided by pi d cube. So in after simplifying, I will be getting it is 8wc by pi d square, where I will be going with the spring index formula. So where K I can able to write as 4c minus 1 divided by 4c minus 4 plus 0.615 divided by c. So which is nothing but the wall factor. So stress wall factor. So with this we will be winding up this video. Thank you.